All right, so we get started here. It's my pleasure to introduce Amir Hakami. He's our SOCAAR speaker for this week. I met Amir when I was at Caltech. He got his PhD from Georgia Tech, from Ted Russell's group. And then he went to Caltech for postdoc with John Seinfeld for 2 years, 3 years?
3 years.
3 years, and then he got a position at Carleton University where he's at now. He's an associate professor there. His research is on all aspects of modeling, from what I saw from the website. He's doing a lot of interesting work on coupling air quality models and seeing how it's a tool for policy making, and also interestingly looking at economic costs of air pollution, which is, I think, is very interesting.
Trying to.
So, without further ado, let's welcome Amir.
Thank you very much. Thank you very much, Arthur. Thanks everyone for being here, and I'm very glad to be here. It is a little bit intimidating to give a modeling talk to a group of people, a number of chemists and experimentalists, but I'm trying to basically show how we can use air quality models, as abstract as they may seem, to inform the decision-making process. But one thing is, I don't know how formal these talks usually are, but if you want to stop me at any time, please do. I mean, it probably helps if there's something needs clarification, etc. I think I have to be on the other side. I don't know how that works with the camera because the keyboard is here. So this is pieces of work taken from the work by my postdoc, Shunli Zhao, and 2 PhD students, one former PhD student and one current PhD student, Amanda Papin and Morteza Mesbah. So, okay. Just a brief outline. I'm going to talk a little bit of background about models and decision making, probably a little bit of history, and talk a little bit about a specific approach to or specific method that we use, one type of sensitivity analysis. Then I'll talk about attributing benefits or damages caused by air pollution to specific sources using that approach. Then most of my talk will be about how those benefits and damages change in a changing world. And I'm going to look at 2 different aspects of change, one being a warming climate and the other one being cleaner environment. There are obviously other aspects that I'm not looking at. And then posing some questions that really remain unanswered after this talk, or even, yeah. So you all know what models generally do. These are essentially large-scale computer programs that integrate governing equations for transport and transformation of pollutants in the atmosphere. And none of this should really come as a surprise to you. The important part is that there are 2 types of, or there are multiple types of inputs into these models. 2 main types, one emissions and one meteorology. We really can't control meteorology much, so the only way that we have to change air quality is through controlling emissions. And the output of models is pollutant distributions, and you can use those for a number of reasons. And people, from the very beginning, when the models, as we know them now, started to exist, people have thought about using these models for decision making, to inform the decision making process. And this is a good example of that. This is a paper. This is a figure from a paper. In 1981, more than about a third of a century back, and these are really the early days of photochemical modeling as we know it. And the 2 guys who wrote this, Greg McRae, basically wrote the first photochemical air quality model as we know it. And Glenn Cass, arguably, is the most influential person in bringing modeling into the decision-making discourse, or into the policy discourse. And what they show is that they looked at the studies back in 1981 of models with different levels of sophistication in atmospheric modeling that were used to make a decision. And also they plotted basically the level of sophistication of the decision model versus the level of sophistication of the atmospheric model or air quality model. And what they very shrewdly observed was that there's this area at the top right-hand corner that we really don't have any studies. We don't have studies, or we didn't have studies that looked at sophisticated approaches for atmospheric modeling and sophisticated approaches for decision making. Of course, this is subjective, but we were interested to see how things have changed since then. So a couple years ago, we tried to populate this plot, the same plot, with the studies that have been done since then, and this is what you get. And the main point is that gap still exists. So we don't really have approaches to get to a high level of sophistication and detail in decision making and atmospheric modeling. And that's really where this talk is trying to get. And I don't claim that I'm going to get to that top right corner, but that's really the objective. So I showed you this picture before, what the general scheme and the larger scheme of the models are, but probably about 15 years or so ago, people started to realize that these models do a little bit more than they were just originally supposed to do, which was to provide four-dimensional distribution of pollutant concentrations, different pollutants and in space and time. And they realized that, or we realized that, with a little bit of modification, they can also provide auxiliary information related to that, and that information really is sensitivity coefficients or derivatives. So in addition to concentrations, we can modify these models to also provide derivatives of concentrations with respect to different parameters. And the parameter that is really, that has the policy weight to it is the emission, because that's, again, the only thing that we can change to improve air quality. So these are now called probably different types of names. Some people call them instrumented models. Some people call them probing tools, etc. But there are versions of air quality models now that are equipped with ways or approaches or methods or tools to calculate derivatives in addition to concentrations. And there are two general ways to do it, or multiple ways to do that, but two general categories of doing so. One group of sensitivity analysis techniques I refer to as forward methods. And what they do is that you focus on one source or one group of sources, and you try to use the model to see how that source or how changing that source would impact different receptors. So for example, you have this power plant, what happens if you decommission it? Or you have, this type of fuel configuration or fuel formulation right now in Canada, what happens if we reformulate fuel everywhere? So what happens if you change one single source, or if you change a group of sources simultaneously but similarly? That is called forward sensitivity analysis. So it basically tells you where the influences from that change is going to go to. A more recent complementary approach is what we call backward or adjoint sensitivity analysis. And that really tries to answer the question that how one receptor or one group of receptors is affected by different sources, by different individual sources. Remember that how receptor changes with source is a derivative. Change in receptor concentration or something else, something based on concentration, like health effects, based on emission rate. This is a derivative, delta output to delta input. This is also a derivative. So both of these are basically answering the same question from different perspectives. This essentially tells you where influences from one source go to, and that tells you where influences on one receptor come from. So it's really a question of perspective. Here you're standing at the source, looking forward in time and space, seeing where things go. There you're standing at the receptor, and you're looking backward in time and space, where things come from. So each one, both approaches have pros and cons. Each one is good for answering specific types of questions. This one is really good. So this one is really good if you, for example, as I said, what happens if you decommission a power plant. This is interesting if you want to know, for example, the influence or the PM that we see on College Road, for example, College Street Road, is coming from what sources? What is the contribution from each source anywhere in Toronto, in Ontario, or in Canada to the concentration of PM 2.5 that we see here? More specifically, the adjoint approach is useful when you are interested in sensitivity to a large number of parameters. But you can use that effectively so long as you can express your policy question that you have as a function of concentration, A, and B, you can express that as a single number. As long as you can condense your policy question into a single number, then adjoint is a very efficient way to look at contributions from different sources. And one example is mortality. This is really, or health damage, which is what I will focus on in this talk. We're, for example, looking at mortality nationwide in Canada or in Canada and US. This is a single number, and we can get contribution to that. If you want to know mortality at different locations, that's not a single number, and this approach is not suitable for that. There are other examples of this as well. One example is the total deposition into a lake, for example. There are attempts to define attainment or non-attainment of the standards based on a single number, or the percentage or the risk of attainment or the risk of non-attainment as a number. Crop damage by ozone, for example, is another application that people are looking at, etc. But again, the problem is that you have to be able to define your policy concern or express that in a single number. And that function is called adjoint cost function. That's, I don't know why they call it cost. It doesn't really have any monetary value to it, but they call it adjoint cost function. This is pretty much the introduction for that we need. I'm going to show results for a continental domain that is fairly coarse for regional models. This is a 36 kilometer, and most of what I'm showing are really, for that reason, should be probably regarded as a first study or proof of concept or anything something along those lines. This is done with the adjoint of US EPA CMAQ model, which I developed a few years back, and it's only for gas phase, so I'm only looking at ozone and NO2 in Canada, because in Canada, NO2 is considered a mortality agent, not so in the US. So when you're defining a cost function over the US, I don't consider NO2, but in Canada I do. So I don't consider PM. Right now, we have been developing over the last 4 or 5 years with a large number of people, mostly in the US, the adjoint for the aerosol phase, and this is near completion, but these results so far are only for gas phase. So what I'm looking at, when I say sensitivity, I mean sensitivity to NOx emissions. I'm only looking at sensitivity to NOx emissions. VOC numbers are also there, but I'm not showing them because they're not that significant. And we do this for 5 years during 2007, the 5 years being the ozone season, May to September inclusive. Again, wherever this is not clear, please stop me. Okay, let's first look and see how we can actually use this approach for health effects. So if we define our adjoint cost function that I'm showing here with J as the mortality associated with short-term exposure to ozone, then epidemiologists have this equation, this nice equation that, other than that last term, basically tells you the change in mortality as a result of a change in concentration of delta C. The parameters that you have there, this is the population at each location. This is baseline mortality rate, non-accidental mortality rate, which is how many people die in that location. And usually epidemiologists use risk of air pollution mortality or express it as a fraction of baseline mortality rate, which is why that number is there. That risk is this beta or concentration response function, which comes from epidemiological models. And what we were interested in doing was to actually monetize that value, put a dollar value on that, and we are using this parameter called value of the statistical life. It's not value of life of any single person, it's the value of the statistical life. And it's essentially a measure of how much people are willing to pay, or the societal average is willing to pay to trade for reduced risk of mortality. How much they would pay to have a lower risk of mortality. And there are many ways to do that. The numbers in Canada, I don't remember them exactly, but in the US it's in $8-point-something million. In Canada it's just under $7 million in recent numbers. The numbers that we have used here are a little bit less because they're $2007. But it's established way to evaluate something that is not really tangible, which is the value of life. The reason that we are doing this, obviously, is that the cost of pollution control is readily available in dollar. But for a politician, it's difficult to compare that cost. Maybe it's easy, I don't know, but it's not as straightforward to compare that cost, that money that has to be spent to reduce emissions with lives saved. Is it worth it or not becomes a very subjective question. Converting it to, or monetizing it, would help basically comparing apples and apples, but there's quite a bit of uncertainty in that number, obviously. The concentration response functions that we are using come from fairly established literature, but again, with a large degree of uncertainty. And I think that's really it. If you have questions, please stop me. So this is what we come up with. This is one example of what we can come up with. So what you see on this map is the cost of driving, or the benefit of removing one typical car, one average car or vehicle from any road in any location in North America. So if you have a value of like $800 like you do in Mississauga, it means that if you remove an average car from the roads in Mississauga, the benefit to the societal benefit to Canada is going to be $800 per year. It doesn't mean that the benefit is going to happen in Mississauga or in Toronto anyway. We won't know that from this approach, but the benefit to Canada is going to be that much. And the same thing for any number that you get. You would see that there are actually some negative numbers in the US. And being in a group of chemists makes it very easy to explain. Those are places where you have a NOx-inhibited environment, so reducing ozone would actually increase. Reducing NOx would actually increase ozone. In Canada, fortunately, for policymakers, we don't have that problem because NO2 is also a mortality agent. So if you titrate ozone to NO plus ozone, you're creating that NO2 that itself is causing mortality. So this benefit, that negative effect, is canceled by the positive effect that you will have from reduced NO2 concentration. So you don't really see those negatives in Canada as much as you do in the US, which is a really important thing because those negative values give politicians in the US a lot of headache. It's very difficult to say that I'm going to reduce NOx emissions when you're actually showing that reducing it has this benefit. Or if car companies can argue that why wouldn't you just increase emissions in New York City to incur a health benefit? So if these numbers are quite large. Remember that we're talking about a typical vehicle. So there are vehicles that are much more polluting than the typical value, and it's interesting that those vehicles are actually likely to be worth less in monetary terms. So it's quite possible that you can have vehicles, a good fraction of the fleet, that are actually worth less than their annual damage that is caused by their emissions. If you put the ridership numbers together for the Toronto Subway, you get a benefit of about $130 million based on this. And all these numbers are really underestimates because we do not consider morbidity or non-fatal health effects. We do not consider PM reduction that comes from reduced NOx emissions. And also we don't consider long-term exposure to ozone or mortality associated with long-term exposure. So this is really should be on the lower end of things. If you actually do this for point sources, for example, this is what you will get. And now, instead of expressing this per vehicle, I'm showing them per ton of NOx emissions. And in economic terms, this is called marginal damage. EPA likes to call it benefit per ton. What it is, it's the reduction in damage that you would get or the increasing damage that you would get for any additional ton of NOx that you would put in the atmosphere. So if you have a value of, for example, $40,000 in one location, it means that if you add 1 ton of NOx emissions in that location, the overall health or overall damage in North America is going to be increased by $40,000. You see that you have large numbers in California. It doesn't mean that there's a lot of damage there because there's actually not many there aren't many point sources in there. If they were, that would have been the damage. This is just regardless of the fact that the point sources actually exist there or not. If they exist there, that's the damage that they would cause. Marginal damage is a very important economic metric because it essentially tells you what is the cost of pollution. And again, that's what you can compare when you're trying to come up with a decision whether you are whether you should go with reducing pollution levels or not. And as you see, the numbers are fairly substantial. And you will know that they are substantial if you compare them with the other side of the other economic metric that is very important, which is marginal cost. So marginal cost is the opposite of marginal damage. Marginal damage is the damage caused by one additional unit of emissions. Marginal cost is the cost of reducing one additional unit of emissions. So this is abatement cost, the cost for reducing 1 ton of emissions. This is the cost to the society of adding 1 ton of emissions, or the benefit of reducing 1 ton of emissions to the society. And if you look at these comparisons, it's quite interesting. First of all, this scale for the damage is 1 order of magnitude larger. And which basically tells you that I should mention that these dots are for the major power plants in the Northeast. So each dot is essentially 1 power plant. If there are more than 1 power plant in one grid cell, then they are averaged together. So each dot on the right tells you how much 1 ton of NOx emissions from that power plant is going to have. What's the societal burden of that emission? And on the left, how much it's going to cost that facility to reduce its emissions by 1 ton. And they're obviously much larger. And this is not surprising. This is consistent with what everyone finds out. Just to give you one example, there are a bunch of power plants along Ohio River Valley, which is here. And you see that their damage is probably in the range of $8,000 to $16,000. On average, they have a damage of $11,000 per ton of NOx. Those power plants in the Ohio River Valley were part of the NOx cap and trade system, which is an emission market. And back in 2007, the permit price for that market was $900, meaning that those power plants could buy 1 ton of NOx, the permit to emit 1 ton of NOx for $900, while the average damage is about $11,000. And again, remember that this is the lower estimate because it does not include PM, it does not include long-term effects or morbidity. So these are substantial numbers, and I think that the disparity between costs and or abatement costs and health damages or health benefits are quite substantial and very telling. So this is all nice. The question, the main part of the talk really here is that how this changes as things change in the world. And first, I'm going to look at what happens to these marginal damages or marginal benefits, depending on how you look at it, in a warming climate. So we do expect that in a warming climate, ozone would increase. And this is generally referred to as ozone climate penalty, because this is a penalty that we expect to pay for warmer climate. So it's a side effect of global warming. And there have been observational studies of that. A paper by Bloomer et al. A few years ago, they basically in Northeast, they came up with a range of about 1 to 4, 1.1 to 3.6 ppb per Kelvin in Eastern US. What they did find that was interesting was that this climate penalty, which is essentially the slope of change in ozone with temperature, has decreased between 2002 and 2007 when very aggressive NOx emission reductions took place in that region from power plant industry. So we are going to look at model-based CPFs, because remember that climate penalty is the slope of ozone with respect to temperature, and a slope is a derivative. So we are going to look at adjoint-based climate penalty factors for 2 different types of cost function, one of them being mortality, so how mortality from ozone changes if temperature increases. And also the other one is that the average ozone in polluted regions. So essentially, the average ozone that we have in areas where we are likely to be above the old Canadian standards, was still current, or what could be the next U.S. standard the next time that the revision is due in December. So the way to do this, sorry about the math, just to basically very briefly explain this. So we are interested in change in mortality or that average ozone concentration, whatever the adjoint cost function or J is, with changes in temperature. So with chain rule, one way is to look at the change in mortality with all species and multiply that by the change in concentration with temperature. This is how the cost function or our mortality or average concentration is going to change through changes in reaction rates that are temperature dependent. We can also do it based on rate constant. Both of those would work. We took the first path, and this is how you calculate it. This really is essentially the adjoint variable that comes from your adjoint model. This is something that we can calculate using a forward sensitivity method, which we call tangent linear model or the decoupled direct method. But this comes from a forward sensitivity, this comes from a backward sensitivity. You combine them together, you get that sensitivity to temperature from rate constants. As temperature increases, the amount of water vapor that the atmosphere can hold also changes. And people have suggested, and climate studies have suggested, that relative humidity is going to stay the same, but since temperature is increasing, the moisture content is going to increase. So you can do the same thing, the chain rule. Again, this comes from the adjoint. This comes from the TLM, the derivative with respect to water content. So how water content is going to affect chemistry, essentially. And this basically comes from thermodynamics, just differentiating the Clausius-Clapeyron equation for water vapor in the atmosphere. And finally, the third pathway is how temperature is going to change biogenic emissions. And the way that we do it, this again comes from the adjoint. And this is changing emissions of biogenics with temperature, which is done through a biogenic emission modeling. And we do that in an emission model, which is called a smoke. So we just run the emission model with the new temperatures, with the increased temperatures, and calculate that derivative that way. So these are the three pathways that we look at. And people have looked at the same pathways before, but with different approaches. And this is what we're going to get. Let me just explain what these numbers mean. So this is ppb per Kelvin. So if you have a value of 2 ppb per Kelvin, for example, here, what it means that if the temperature at that location increases by 1 degree, then there will be a 2 ppb increase in polluted regions concentration somewhere. Where that 2 ppb increase is going to materialize is not something that, again, we know from here. And if you do this, the average, and you average this over the entire domain, you get an average of about 1.3 ppb per Kelvin, which is in range with the observational studies that I showed you for Bloom et al. If you do it for Northeast. If you do the same thing with mortality, you get the numbers. Again, if you have a number of, for example, 1, it means that if temperature in one location, if in one location you have a value of 1, means that if temperature in that location increases by 1 degree Kelvin, there will be 1 additional mortality in North America per season due to that increase. So if you have temperatures increasing by 1 degree everywhere, that adds up to about 370 deaths, additional deaths per Kelvin per season. So for mid-century 2 degree increase in temperature, you're looking at something in the order of, I don't know, about 3,000 probably, approximately, back of the envelope, 3,000 additional deaths. Just to see where that change comes from, if you look at different pathways separately, this is what we get for polluted region concentrations, if that's our cost function, and if our mortality is our policy question. And for mortality, through this pathway, we get about 260 of that 370 deaths. If you look at water vapor, which is really the interesting one here, overall, it's a negative value, which is expected because water vapor reaction with O singlet D is the net loss, a global loss of ozone in general. But you do see those dots in urban areas that are positive, which is, again, not surprising, but they show up very nicely. That's where, even though it's a loss to ozone, in that radical starved environment, that O singlet D water reaction that produces OH goes a long way to produce ozone in reaction with other organic compounds there. And that duality is really what drives those urban areas, or separate those urban areas from the rest of the domain. So overall, about minus 200 deaths from that pathway. And the third pathway being biogenic emissions. Again, you have them more significantly in urban areas, both for polluted regions and mortality, which is understandable because they are NOx limited, they're NOx inhibited or VOC limited, so having more VOCs has more impact in NOx-rich environments. So all this is nice and fine, but what do we really get out of this? The interesting thing here, to me at least, is that if you look at areas that are really significant, this is the total polluted region climate penalty factor. If you look at the areas that are very large, those are really NOx-rich regions, and to large degree because of the behavior of the water vapor, but also because of increased effectiveness of biogenic VOCs in producing ozone in those areas. So if you were to reduce NOx emissions, these areas would become more like the rest of the country, which means that that heightened sensitivity to a warming climate would disappear. So if you control NOx, and if you make regions to, or if you make the spatial heterogeneity in NOx availability to disappear to some extent, then you are basically going to make this very vulnerable environment or locations, or very sensitive locations, to also disappear. This makes us argue that reducing NOx, although it has nothing to do with climate change, in fact is a climate change adaptation with respect to air quality, because it reduces our overall vulnerability to a warmer climate, because we won't be as sensitive to temperature increase as we are currently in high NOx environments such as urban areas. And we have seen that observationally with reduced NOx emissions from power plants. That's why the observational studies show that CPF has dropped because of lower NOx emissions. So this is not news, just that we're seeing it. And I think it's particularly important for urban areas, which also opens. So one is that, in my opinion, you can argue that NOx control could be an adaptation strategy because of that. Also, the most sensitive places, or the places that would benefit mostly from this reduced vulnerability, are urban areas where we already have a disbenefit for NOx reduction. So a lot of the policy resistance to reducing NOx emissions in those places is that there's a disbenefit. If you reduce NOx, ozone will go up. But an indirect benefit that comes with reducing NOx is the reduced vulnerability in those areas, and it would partially compensate that disbenefit that we would that we have. And finally, I think this would be also interesting to see what the impact of urban heat island is, because urban areas that have high NOx environments actually have higher temperatures. We already know that. We are looking at higher temperatures because of the climate, but in reality, those urban areas already have higher temperatures because of the urban heat island effect. I'm sorry, that should not be there. That's what happens when you recycle presentations. So what happens when, so that's the change in climate, or going to a warmer climate. What happens if we go to a cleaner environment, if we aggressively and progressively reduce our pollution levels? So let me just talk a little bit about economics before I talk about that. I talked about marginal cost previously, which is the cost per unit emissions at different emission levels. As you go to lower emission levels, meaning that you control your emissions more and more, the cost of control goes higher. It becomes more expensive to control more. Zero emissions is going to be very costly. This is quite intuitive, but also traditional, conventional economics. The damage is expected to go down. And this is really, so you go to lower emission levels, economists say that damage will go down. And this is because the environment has a natural capacity to cleanse itself and to protect itself. So at low emission levels, it's going to take care of the pollution. But as you add more and more and more pollution, at some point you're going to overwhelm the environment, and the damage gradually starts to pick up. Again, this is traditional environmental economics. The importance of these two curves, the blue being marginal damage and the red being marginal cost, is that where they cross is the the optimal point that we want to be. So all the value, those numbers that I showed you, the marginal damages that I showed you, were for the current level. So I showed you where things are, where the damage is. So I basically showed you this point for different locations, right? I showed you the damage at different locations. And I showed you the cost for power plants, for example. But the question really is that how these things are going to change. And the importance is that that cross point is the point of economic equilibrium. That's the optimal point that you want to be from an economic point of view. Emissions higher than that cause more damage, so you have economic justification for reducing the emissions further to that level. But if you go further than that, you really don't have any economic justification because the cost of control is higher than the damage inflicted on the health or environment. So that's really where you want to be. That's where you're going to design your policy to be. So the question that I'm asking here really is that with what rate marginal damage is going to decrease as we go to lower emission levels. So what is the rate of decrease in marginal damage? The answer is that it doesn't decrease. In fact, it increases. And being in a room with many chemists, it's so easy to explain. I don't know why economists thought that this would increase. Sorry, that this would decrease. If you go to a cleaner environment, any NOx molecule that you add is going to have less competition to produce ozone. So obviously it would be more effective in producing ozone. So the effectiveness per molecule or effectiveness per ton is going to increase as you go to cleaner environments. Again, this is contrary to anything that you see in environmental economics. And the reason for that is that that model of decreasing marginal damage with pollution level was really about primary pollutants. That if you reduce their emissions, the concentrations will go down. That's really where it was. But somehow down the road, nobody knows where, this got basically extended to secondary pollutants like ozone, but also to PM, to secondary PM, organic or inorganic. But it simply isn't true, at least for ozone. We haven't really checked that for PM yet. Just to show you one example, these are values for 4 major power plants in the US at different levels of emissions from point source emissions. So as you basically, maybe I should have flipped this scale, but this is basically 100% control, 80% control, 60% control, etc. As you go to lower emission levels, you see that actually marginal damage increases and increases significantly for some of them. The same is true about point sources, about mobile sources. As you reduce mobile emissions, then all of them, and this is invariably true, every type of source everywhere increases. Marginal damage all the time increases. So there's no exception to this. And again, from a chemical point of view, there shouldn't be any exception to this. As you reduce mobile emissions, again, marginal damage increases. For a city like Los Angeles, it's actually quite significant. These are old results, and they only include on-road mobile emissions. Now, we have included non-road mobile emissions, and these increases are actually quite more significant. So this is actually very mild compared to what we are seeing with all mobile source or all mobile emissions included. If you look at reductions in both point sources and mobile emissions, this is the average domain-wide value that you get. That quite sharply, these marginal damages increase as you go to lower emission levels. Why is that important? Back to this point. This was our optimal point of economic operation, where we want to get with our policies, with a decreasing marginal damage curve. If our marginal damage is actually increasing, we are going to, our optimal point, our equilibrium point is going to be here, which is quite further or further. How much would depend on the shape of those plots, but it's further than what we already think it would be. So if with an increasing marginal damage, we have to be more aggressive in our emission control to reach the point of economic equilibrium. That's essentially the message. So the conclusions being that what we see in environmental economics textbooks, not correct for ozone, and the slope or the increase is actually quite substantial for a lot of sources and a lot of places. Overall conclusion, significant NOx control, significant benefits from NOx control when it comes to ozone. But interestingly, in polluted regions, there is a secondary benefit from reducing NOx emission that comes both from the interaction with climate, but also from the compounding effect that you have with reducing emission levels, because any ton of NOx that you reduce has a benefit, direct benefit, but also it makes future reductions or future tons of NOx reduced more valuable because of an increasing marginal damage value. Okay, just some of the examples of other things that I think are worth looking at when our group is looking at. So everything that I showed you is from about ozone, but we are basically developing an adjoint with a number of other researchers in the US and in Europe, actually. We're basically extending this to aerosol processing in CMAQ, and after having that, we can have the same type of analysis for aerosol species. These the values that I showed you were average values for the ozone season. If you look at day-to-day values, they are very different. There's a lot of fluctuation. When you develop policies based on those average values, right? But the large-scale fluctuation basically tells you that your policy is not going to be effective on any specific day. So there are days where your policy is completely ineffective. We now have the ability to forecast sensitivities in addition to concentrations. So when we run a forecast model, we can actually see what are the sources that are going to contribute to mortality in Toronto tomorrow, or to AQHI in Toronto for tomorrow. And if tomorrow is a bad forecast day, then we can target those sources and try to reduce those emissions. It doesn't have to be a forced reduction, but you can basically have a campaign where you enlist emitters that they would voluntarily take part. And some preliminary results shows that just a few % change in emission behavior can go a very long way in pushing you below attainment level, or below the level of AQHI that you consider safe, etc. AQHI being Air Quality Health Index. One other area that we are looking at is, so we are going to go through reduction in greenhouse gas emissions. A lot of those greenhouse gases have co-emitted criteria pollutants like NOx. So if you reduce greenhouse gas emissions, you're likely to also, from specific sectors, you're also reducing NOx emissions from those sectors. Now, the benefits of reducing greenhouse gas is uniformly distributed because they live such a long time that it doesn't really matter if you reduce the GHG in Toronto or in New Delhi. So there's no difference in there. But the air quality co-benefits could vastly be different. Because right now there is no spatial heterogeneity in benefits, what really will decide how we reduce emissions of greenhouse gases is the cost, right? But if you include co-benefits, and people have shown that this could actually be larger than the cost of greenhouse gas reduction, if you include that with the spatial heterogeneity that we see from adjoint results, then you actually can have a new level of complexity added to to where you're going to control your greenhouse gas emissions, because now the benefits are spatially heterogeneous. So not just the cost, but also the benefits. So that's another area that we're looking at. All these numbers are nice, but everything that I showed you is essentially wrong. As modelers, we know that all our numbers are wrong. The question is that how wrong they are. And that really goes back to the confidence, the level of confidence that we have in our results, or uncertainty associated with our results. And as a community, we have been extremely lazy in providing uncertainties and in characterizing uncertainties associated with our modeling results. And it starts in many different places, but most importantly from emissions. So one area that we're working on right now is that as we prepare emission inventories, we want to also prepare an inventory of uncertainties that go into, of the data that goes into that inventory, so we can propagate uncertainties to our emission model. So when we actually have emissions, graded emissions for models, we also know that what is the uncertainty for each species from at any location. And that has a number of different uses. Obviously, it has a decision-making use, because then you can propagate those uncertainties through your air quality model. But it also has use in inverse modeling applications, because we don't really know the error characteristics of our emissions. So I showed you those marginal damage information. So right now, for example, there are cap and trade systems in US, currently in US, and also in Ontario, not very effective. And the new ozone rule in US that is still going to go to the court and then get sued, basically will go through the litigation, I think, in the next 2-3 years. But they encourage state or regional cap and trade systems for reducing greenhouse gas emissions. Cap and trade systems are very good for minimizing the cost to the industry, because they essentially divert the cost of control to emitters and to facilities where control is the cheapest. That's what the market does. But they don't really have they don't account for any type of environmental or health performance. If you include the cap and the marginal or the health damage information that we have into the cap and trade system, or into any type of economic instrument that they have, then you can basically take advantage of that information and shift them to more environmentally beneficial performance. One way to do that, and we have experimented with this, is to assign, so cap and trade right now trades 1 ton of emission in this location with 1 ton of emission in that location. So instead of doing that, you can trade emissions with an exchange rate. Same way that you have an exchange rate for currencies. If emissions in this location is going to cause more damage, then it's reasonable to expect that you would trade it as a more valuable commodity, and so on. So that's basically trying to change or improve economic instruments such as cap and trade is another area. And one other area that I'm particularly interested in is that all this information, this economic information, is trying to help you come up with a more more cost-effective approach for reaching your objective. But in the US, but also in Canada, a lot of decisions are really made based on attainment. So it doesn't really matter how many people are living there. You will still have to attain your standard. And it's a very significant philosophical question. And people have been talking about this for a long time, but I think now we can probably put a little bit of different angle to it, that which one really is more important? Is it attainment or exposure? So should we value improving air quality for Toronto more than we would value for, I don't know, middle of nowhere? Ottawa. We have someone on the phone from Ottawa. It's not just me. It is a very fair question, and you can't necessarily say that no, Toronto should be more important because there are arguments to be made on each side, and especially in a place like U.S. that they have the federal structure that you have a Senate that each state gets the equal weight in vote. I think that becomes even more of a reasoning. But that's another area that I think would be is interesting, and we are going to look at. So with that, I end, and if there's anything that I can explain or any suggestions and comments, I would be happy to have it.
Any questions for Amir?
So this relationship of costs to emission reductions is dependent on the shape of the response curve of ozone and NOx.
Yes.
So why would you expect PM to do the reverse? There wouldn't be that nonlinearity in PM.
So the shape of, okay, correct me if I'm wrong, but the shape of ozone to NOx, in most cases, not all the time, but is concave, meaning that you get saturation. If you go to higher levels,
right,
you would get saturation. And I think that's for anything that is chemically controlled, you would get that, isn't it?
For the, I was wondering about the same thing. So for the nitrate from NO2, if we speculate that nitrate actually has a toxicological consequence, it could be either way. We talk about the oxidants as being the limitation. I think that's what John may be thinking of that. But if it's the ammonia that's the limiting agent, perhaps not.
Yeah.
It could be flat.
I was thinking of something non-reactive like black carbon.
Oh, so
Okay.
if something is
Easier.
non-chemically, so this
Yeah.
only comes from the fact that you have nonlinearity in chemical production,
Yeah.
in chemical efficiency,
Right.
essentially.
Right.
If you don't have that, then really there's no reason to expect that response to be.
Right.
I mean, it could be usually it's very flat.
Right. Okay.
But I can see that. I mean, I'm not going to say how. Yeah, but this is something that we are going to look at.
Yep.
And I think nitrate is really where things are going to change.
But then it also depends a lot on the shape of your dose response curve too. So
Yes, but that's
something like PM. There was a talk at the AAAR by Cope showing that it might be a logarithmic type response curve.
Yeah. So right now, I think we don't really have enough information to know. So right now, most of the PS studies they really consider that to be a single number.
Yeah.
But again, I don't think we have enough information to speculate with that. But there are theoretical shapes for that, and there are also evidence. And I think Canada is very important in that aspect because the concentrations that we are seeing are lower. So we are actually providing a specific part of the concentration response function that the rest of the world doesn't really get their hands on. The problem is that APS studies from Canada consistently give higher concentration response functions.
Right.
So if anything, this would make it look concave, which means that it would actually enhance that. But this is way too much speculation right now. But there's also this immigrant effect in Canadian APS studies that immigrants to Canada usually really pollute the signal from the Canadian-born population because they have usually a much lower concentration response function than those who have been raised in Canada. So epidemiologists want to speculate about this, but I think one explanation from someone completely uneducated on the topic is that you at lower, basically at higher concentration, you develop a little bit of, you will be less sensitive to changes in concentration as you would in lower concentration
Well,
levels.
it's like cigarette smokers. If you extrapolated air pollution up to the levels that people breathe in, you'd die instantly.
Yeah.
And let me add to that. So I think Burnett's paper, which is the cigarette and secondhand smoke, it is showing this asymptotic.
Yeah,
type
that's
of
what I meant to say. Not
Yeah.
asymptotic.
And I think there are some studies from Canada that are coming out. I was looking around to see if Jeff was here, because I was a co-author on many of them. But, his nephew Jake is here, so we'll go with that. What they show is exactly as you say, that there is greater sensitivity at lower concentrations, which is very different than what we've seen for PM. So I'm really wondering about if your conclusions, when you look at PM and you look at NO2, you're going to find the exact opposite of what you're suggesting here. The idea that reducing NO2 is likely going to have a fair impact on the PM. And
why NO2? So PM, I think I can see that it would go either way because there are so many constituents there that could, some of them would behave this way, some of them would behave that way. So this comes down to concavity or convexity of the total damage function.
Right.
So it could end up being convex or concave, and I have no idea really. But we will look into that once we have the answer. But why would you say that for NO2?
Well, I think it depends on, and that's the second part that I want to look at is, I believe what you're doing is you've got a heterogeneous population. I wasn't quite clear, but you were very, very thorough about saying that the emissions occur here, we don't know where the death occurs.
Right.
But, intuitively, we do know the death occurs where people are living.
Yes, but
There's no population, there is no health impact.
Right, but that's why you get negative values, for example, in a city like Los Angeles, because so if you reduce NOx, for example, in Los Angeles, you are going to reduce ozone overall. But locally in Los Angeles, you're going to increase ozone, but more downwind, you're going to increase ozone. Then the negative value that you get is because that local disbenefit is happening in the populous area.
Right.
The benefit is happening in the less populous area. So
for example, because I think we've modeled it the other way. So we look at where are the people being exposed, which is the question. So you have emissions at one place, you have transformation, you have people being exposed, and you look at the benefits or the health detriment in that location, which is the downwind location you're talking about. And I would have thought with your model that you'd be doing the same thing, because you have a chemical transformation.
Well, you are doing the same thing, but where people are exposed is across the entire country. So you can run the same thing, and you say that I'm going to look at people in Toronto, and I'm going to get how they are affected.
Right.
And that probably is something interesting to do, that you basically look at specific receptors, for example, for which you have good history. You have epidemiological history. You have hospital admissions or different types of mortality caused by cause, and then you only look at that point and see where things are coming from actually.
Right. That makes a big difference. If you look at it by census area, the idea of having a coal plant in Toronto is very different than in Beijing, just because of the population density. In Hong Kong, it makes a huge difference what the population density makes a huge difference how many people are living downwind, so what the average wind direction is. So some numbers in terms of how many mortality is the monetized value per ton of NO2, which is one of the values you put there. Well, that is a huge dependence on where that plant is relative to
right, but that is in the model. That is included. So
that is included. Oh,
yes, that is included because. Sorry, I don't.
So you had the plot. I wasn't sure if that was a population distribution plot, essentially.
So if I just go to the equation that we use to get these numbers.
Yeah, you got.
So there is a population there. So at each location, so
each census area.
Each this is to the grid size. So
okay.
This would be in this particular case 36 kilometers. And one very interesting point that we are planning to do for the region of Peel, because they're developing a very high resolution inventory, and that includes the entire GTA, is to basically, they're having a 1 kilometer domain, so we basically want to see what happens if you go from 36 kilometers to 12 to 4 and to 1. Do you really see the same patterns as you go to higher resolution, and what is the value? People have looked at resolution and health outcomes, and usually you get larger values as you go to higher resolution. But here, we are looking at each location's population baseline mortality rate for that specific location. So this is why if you actually look at the plots, they are very close to population centers, because they are driven by, so they're driven by the influence on the population centers. So the population and the location, so things that cause the spatial heterogeneity in those numbers are one, population, two, atmospheric response. Really, those are the main two things that happen. And atmospheric response obviously includes meteorology, but also chemical environment.
So you don't have to go back to the slide, but you were showing that on your last slide, you have the complexity of optimization versus the complexity of the model itself, and then you have this missing region, right? So to me, that looks like that region we're not popular in that region because maybe it's because of computational power, or maybe the lack of understanding of the processes, or I don't know anything about optimization, but maybe it's just not efficient when you use
That's
a
a very good
complex
point.
model, right?
That is a very good point. I mean, there are reasons, because if you see, people have looked at very, sophisticated decision models, and well, this is old, but we have also looked at sophisticated atmospheric models. It's just that doing both of them together is going to be very costly. I mean, some of the works that we are doing really probably go around here, I would say.
So yeah, the question is, do we really want to go there, right? Is it somewhere we want to go?
I would say yes, because the question is that you do get, so I say that we are around here, and by going there, we can show, and I didn't show those results, but we can show that, for example, some of the economic instruments that are informed by marginal damage information, they perform significantly better economically compared to cap and trade, that is blind to environmental performance. So by going there, you gain quite a bit of efficiency, be it economic efficiency, because you can reach the same level of environmental performance cheaper, or environmental efficiency, because with the same amount of expenditure, you get to much better environmental quality. So you do gain quite a bit even with that. And I suppose if you go higher, you would get, this is all about effectiveness, because this is optimization. What is the optimal way? So what we are seeing is that we are getting to better places in terms of air quality, but at an awfully suboptimal pace. I mean, it's just really suboptimal. It's easier to do, and these are very good steps, but there's really no, I mean, cap and trade is a very good example. Cap and trade is a very good example. It's very efficient economically, completely disregards something else.
So you're essentially you're trying to develop a Bitcoin for a cap and trade program.
Yeah, I think that's a good way to put it. But the problem is that this is very difficult to do. So the Agent can't really do this, I would say. Because remember, in the Agent, we see that this is the influence on the nation. But at the same time, you want to make sure that in every location you attain the standard. That's a multi-objective optimization, which does not work very well with the Agent. So there are things that are still very difficult to do.
One were to get very cynical about it, to look at the derivative of decision making versus complexity of input.
Mm-hmm.
One might think that the more complex the information required to make a decision, the less likely the decision will actually be made.
That is also very true.
Yeah. So,
but I think this is also a confidence path for the policymakers, essentially, and they have become more comfortable with some of the things that they were not comfortable with. But it is true. It is very true. And one very important factor is that really uncertainty. I mean, if I'm power plant industry, it's not easy to poke hole in these numbers that I'm showing you, or any numbers. Like we see that we had this discussion with climate studies. It's very easy to basically start poking.
So we're actually way over time, but I think it's okay. It's really nice to see, some of the science actually gets applied to decision making and trying to make a difference in this world.
Yeah.
So let's thank Amir for a wonderful time.